Hello, everybody. Mr. Scala coming at you digitally. So, here in class, we have wrapped up Investigation 8, looking at which we wrapped it up with our freezer design challenge, and now we have started Investigation 9, and we are on 9.1. We're going to be looking at substance models. So, our phenomena is margarine is one molecule away from plastic. So, by just adding one atom to it, we've completely changed it from something that we interact with, that we eat with, to something that we use to hold our water, like plastic water bottles. So that just goes to show you how big of a difference one molecule, one atom can make. So our learning target is I can develop and use a model to describe how the total number of atoms does not change during a chemical reaction. Thus, mass is conserved through structure and function. And like we do every time, we're going to break that down because that's a lot to take in and it doesn't make a lot of sense. So the first part is our science and engineering practices, and that's in the blue. And that's just I can develop and use a model. So a model can be anything. It could be a picture. In class, we have magnets with the different elements on it. We have these little dots that are stickies, that are stickers, so that we can stick them in our binder. Model is very general. So just being able to use a model to describe is our science and engineering practice. And then how the total number of atoms does not change during a chemical reaction. Thus, mass is conserved. What that really means is, let's say we have a chemical reaction, just like the one that we did with our citric acid and baking soda. When we added the water to it, it had a chemical reaction, it created gas. And that gas was carbon dioxide. So our carbon dioxide molecules, so carbon, two carbons and one oxygen, were flying around in the air. They were created. The atoms rearranged. And we lost some of them in the air. But if we were to put the balloon over top, we could capture them. And those atoms have weight. And that is what mass is. Mass is weight. So basically what it's saying is just because they rearrange during a chemical reaction doesn't mean we're losing them unless they turn into gas and we're not capturing it. So the mass shouldn't change before and after a chemical reaction happens. And then through structure and function. And that's just looking at the structures of them and the structures of the atoms that we're looking at. And then the function will be like when the chemical reaction, how are they rearranging? So just a quick review. What is a substance? Well, it's a unique form of matter with unique properties. It's composed of elements. It's defined by the kinds and number of the elements from which they are composed. And it's composed of one, two, or more elements bonded together and can be represented by a chemical formula. So what now? So all substances are made of elements. Particles of elements combine to make all substance, which we discovered that when we looked at our food label. We saw some pure elements in there like our sodium, like our iron, zinc. We even found some copper. But they come together to make things like our citric acid, because citric acid is a combination of carbon, hydrogen, and oxygen. So the basic particles of elements are called atoms. Each element has a unique atom. Up on the board, I had magnets with the different chemical symbols from the periodic table. So like I have a magnetic Na, which is yellow, a magnetic Cl, green, magnetic C, orange, so on and so forth. So every element on the periodic table has its own unique atom. So our focus question that we worked on is, how do atoms combine to make new substances? We answered it in the before box. Keep in mind, there are only 3 wrong answers. Leaving it blank, I don't know, I don't care. You could talk about Bob the Builder using a hammer, a magical hammer, to combine atoms to make new substances. Remember, this is the before box. We don't really know or have much background. So combining atoms. Here's a new particle. We have an O and an O, so 2 oxygens. So how many atoms have we combined? Each of these represents an atom. So in total, we have 2 atoms that we've combined. And then how many elements have we combined? Well, they're the exact same element, oxygen, oxygen, so only 1 element. So we've combined 2 atoms, but only 1 element. And to take it even further, if I add a 3rd oxygen atom, this is a particle of a substance that we call ozone, and it's made up of 3 oxygen atoms. So again, we're just looking at the number of elements and the number of atoms. So is ozone an element? Ozone is a molecule made of 1 element because it's only made of 1 atom. So it is an element. If we're looking at it, we have our 1 oxygen, 2 oxygen, 3 oxygen. So we have 3 atoms, but only 1 element. So So right here, we have an atom, a compound, and it's made of 3 different atoms. You have 1, 2, 3. So it can't be an element because it's made up of 2 different things. Remember, an element is a pure substance that can't be broken down any further. So we have 3 atoms, but how many elements do we have? If we're looking at it, we only have 2 elements. We have hydrogen and oxygen. So there are 3 atoms, 1, 2, 3, but there's only 2 elements. So this is a representation of a water particle. It's a combination of 2 hydrogen atoms and 1 oxygen atom. Any particle made up of 2 or more different kinds of atoms is called a compound. So, how many elements are on the periodic table, including compounds? None. They're all elements that contain 1 atom. But what we talked about in class is if we're looking right here, we can see the total number of elements are 118. And a compound is just a mixture of elements. Like we talked about with the margarine. If you just add 1 molecule to it, you've created something completely different. 1 atom to it, you've created something completely different with plastic. So, and it's just any combination. So with our 118, there are so many different combinations, millions and millions of combinations we can make of different substances to make different compounds and any mixtures. So all matter is made from atoms, the basic part of elements. So there are over 90 different atoms on Earth from which all the substances in the world are made. So atoms combine to make new substances. If particles of a new substance are made of 2 or more atoms of one kind, the substance is still an element. If the particle of a new substance made of 2 or more different kind of atoms, the substance is a compound. If the atoms in a particle are connected together with a strong bond, the particle is a molecule. Carbon dioxide is an example of a molecular compound, while hydrogen is an element compound. If the connection is weak, it is an ionic compound. Sodium bicarbonate is an example of an ionic compound. And right now, since we're just working with this, we're not too focused on what the difference is and looking at, is it a molecular compound? Is it an ionic compound? How they're bonded together. We're really focusing and looking at chemical formulas and looking at how many atoms are in it, how many elements, and how do we know that? So what we worked on today in class was we went into our binder and we looked at how we can represent simple substances using we have these little dots that are stickers and we stuck them in our binder. So with our carbon, the way we could represent that is with our orange dot. So 1 orange dot. And if we're looking at it, the number of elements in there, that's just 1. There's just 1 element, it's carbon. And the number of atoms, well, there's just 1 there as well. So let's see if I can get a better picture. Here we go. So this is what we worked on. We represented it with our C, and there's 1 element and 1 atom. Then we looked at water, which is H2O. And this 2 here is a subscript, and it only applies to the one in front of it. So H2O. So we have 2 H's and 1 O. 2 H's, 1 O. And the number of elements, well, 1, 2. Only 2 elements. But there are 1, 2, 3 atoms. And if we look at carbon dioxide, CO2. The 2 means there's going to be 2 oxygen. And since there's nothing with the C, there's just 1. So we have 2 oxygen and 1 carbon. So we have 2 elements in it, carbon and oxygen, but 3 atoms in total. And the next one we looked at was sodium chloride. If we're looking at that, we have NaCl. So the Na is 1 atom of sodium, and the Cl is 1 atom of chlorine. So you have NaCl. So there are 2 elements and 2 atoms. 1, 2, 1, 2. Oxygen. So that is represented by O2. So our drawing has 2 oxygen atoms. 1, 2. But there's only 1 element in that, oxygen, but there are 2 atoms. And a fun one, sodium carbonate, Na2CO3. So just looking at our formula here, Na2. So we know we're going to have 2 sodiums. C, there's nothing there, so just 1. And then O3. So there'll be 3 O's. And we talked about this in class, and there is a correct way to draw these. Right now, we're just becoming familiar with them. I don't expect you to know exactly how every single thing is drawn. It's fine if you put them in, a different order, or you're drawing, they're not lined up just like this. So we have our C in the middle here for 1 carbon. Then we had 3 oxygens, 1, 2, 3. And we had 2 sodium atoms, 1, 2. So right here it's asking, what is the total number of elements that we used? Well, we have Na, C, and O. So we only used 3 elements. And this is asking how many total atoms do we have? And that's just simple counting. 1, 2, 3, 4, 5, 6. And that's what we worked on today in class. Thank you so much for tuning in. Have a wonderful day. Hopefully I'll see you soon. Bye.